welcome. So this is unit 2. We're going to talk about heat in this section. And we're going to start talking about heat by looking at this hot bowl of soup. If you have a hot bowl of soup or a cup of hot chocolate and you want to cool it down, you can do two things. We can blow some air over the bowl and we can put an ice block in there so that as the ice melts, the soup gets colder. In the first case, we are cooling down our soup through a process called evaporation. And in the second step, we are actually cooling down our soup through the transfer of heat energy from the warmer soup to the colder ice. In either case, we have this transfer of heat affecting the kinetic energy of the molecules. So heat and energy are related. When we push a desk on the floor, if we look at this picture, the molecules at the bottom where the desk, the leg of the desk is in contact with the floor, will tend to vibrate more as they get more energy from that. If you rub your hands together, you'd actually feel the palm of your hands heating up. And so we are changing the energies of the molecules that are in contact when we do these different exercises. So when we talk about the energy that an object has, we're talking about the external energy. We already talked about the fact that energy and work are related. The work done is the same as the energy used. But here we're going to describe the energy an object has in terms of the external energy because of its motion or because of its position. But there's something more. There's the energy of its molecules. And the energy of the molecules is what we call the internal energy. And that is a little bit different in how we classify that internal energy compared to the external energy. For example, if the desk is moving with a certain speed, we will have some kinetic energy. That has nothing to do with the molecules themselves. The internal energy inside that make up the particles of the desk is what's described by the energy of those molecules themselves. So the process of increasing internal energy is called heating, and that's how heat and energy are related. When the internal energy increases, the heat of the object increases. And of course, we associate heat with temperature. When we have more internal energy, we have higher heat, we have higher temperature. So the temperature is a measure of the average internal energy of the matter. Heat is a measure of the internal energy that has been transferred from one body to another body. So temperature is not energy. Temperature is just a measure. It has a reference scale, and it's just how we measure whether something has more or less energy than another substance or another matter, but it's not really the actual value of the energies themselves. So while we have increasing internal energy, we call that heating. We can have decreasing internal energy. We can call that cooling. And that's when the molecules in the substance actually start losing energy and start to settle down and not move as much, sort of going from a liquid to a solid. So we can have that, for example, if we have water, we put it in the freezer, we make ice. Of course, when you take your ice out, it doesn't move as much as water because the molecules themselves are not moving as much as the water molecules are. And so the molecules of ice will have less kinetic energy than that of water. Let's make some notes on heat. Heat is a form of energy. And so because of that, the heat of energy, the unit of energy is also applicable to the unit of heat. We use that unit of energy as joules. So a joule is also a unit for heat. But here I want to bring us to a new type of unit for heat, and that's called a calorie. And a calorie is the amount of heat that's required to raise the temperature of 1 gram of water by 1 degree Celsius. So if you can think of taking up 1 little gram of water, putting it on a little heating element and then measuring how much heat we need to add to raise that 1 gram of water by 1 degree, that's going to be equivalent to a calorie. When we have calories, the base units, when we have meters, we can have a kilometer. So if we have calories, we can also have a kilocalorie, and 1 kilocal is the same as or equal to 1,000 calories. A kilocal is also 1 food calorie, and we write that food calorie sort of with a uppercase C. So 1 kilocal is 1 uppercase C in calorie. Note that the calories we use for the unit of heat is just a lowercase. When we're talking about food calories, it's the uppercase C. And that's just because it's the format that's been used to describe the two different types of calories. So while 1 calorie is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius, 1 kilocal is the heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius. So we have a kilocal for 1 kilogram and a calorie for 1 gram. In either case, we're raising the temperature of this amount of substance by 1 degree Celsius. So the unit of our food calorie is the big cals, the uppercase C, and we talked about that fact that 1 calorie is 1,000 of these lowercase cals, which is our unit for heat. And we get food calories by looking at heating up the amount of or burning the food and looking at the heat that's released when that food is burned. So that's how we get food calories. So if you take your package of Oreo or a package of Cheetos and you turn to the back, you would see the number of uppercase C or calories that is in each serving of that food. And that energy that's written there is really the value of the heat that is released if we burn the food. And that's how we can determine the energy content of the food from the heat that released, because we just saw that heat is related to energy. So since both joules and calories are variable units for heat energy, we can convert between joules and calories. So 4.184 joules is 1 tiny lowercase calorie, which is the unit for heat, or 4,184 joules is equal to 1 kilocal, or like we said, that's the same as 1 food calorie. Now let's do some kitchen physics. Let's say we have this stove and we want to put some water to boil on that stove. We can ask some questions. The first thing, let's say we want to find out how much heat we need for that pot of water to boil. Well, we know that we can consider the following 3 things. One thing is the initial temperature of the liquid. Are we starting with cold water from the refrigerator? Are we starting with room temperature water? Or are we starting with hot water from the tap or the faucet? So the initial temperature is going to tell us how much heat we need to add to this before it comes to a boil. The second thing, besides the temperature, is how much of the liquid is in the pot. As you can imagine, the less liquid we put in, the faster it'll boil, because we have less of it to get up to the temperature we need. And the third thing is, well, if it's water or if it's soup, how can we compare them, right? So the kind of liquid will determine how much heat energy we need to add to raise that temperature or for it to boil. So just remember those 3 things: initial temperature, how much liquid is in the pot, and what kind of liquid are we boiling. So based on these 3 different questions that we can answer, we can calculate what's called the specific heat, or the heat that's required to change the temperature of the liquid. So when we're talking about the initial temperature of the liquid, we know that the initial temperature is going to affect how much heat we add. More heat is required to raise the temperature by more degrees Celsius. So if we're starting at 1 degree Celsius, we're going to have to add more heat to bring it up to 100. If we're starting at 50 degrees Celsius, it's less heat than if we started at 1, right? Because we're already halfway to 100. So the heat, Q here, is what is the symbol that's used to represent heat energy. So Q, the heat energy, is proportional to the change in the temperature. The bigger that temperature changes between where you start and where you want to end up, the more energy that we will need. The larger the mass, the more heat is needed to change the temperature. So if we have more liquid in the pot, we increase the mass. And if you can imagine having to boil a small pot of water, it will happen faster than if we have a really huge giant stock pot of water. So the larger the mass, the more heat is needed. And so we can say that the heat, or Q, is proportional to, that's a proportional sign, to the mass. And then different types of substances require different amount of heat energy. And that is what we call the specific heat. Each type of substance can heat up easily or take longer to heat up, and that's just the nature of how the molecules in that material is. And that, so we call that particular type of characteristic of a material the specific heat capacity, and that's given by the lowercase c. So when we put it all together, Q is the heat energy is equal to the mass times the specific heat capacity of the substance times the change in temperature, right? M is the mass of the matter, the mass of the substance, and normally that's in kilograms. And the specific heat capacity is a constant for the particular type of material or matter. And so that's in kilojoules per gram degree Celsius, or calories, kilocalories per kilogram degree Celsius. So here we have some specific heat capacity of different substances. You see, this is the constant C that is described in the equation before. And the unit here is calories per gram degree Celsius, or kilocalories per kilogram. So the kilos kind of work together, kilograms per kilogram, or calories per gram. So if we look at the table, air has 0.017 calories for every gram of air that we want to change the temperature 1 degree by, whereas water has 1 calorie for every gram of water we want to change the temperature by 1 degree Celsius. So in this list of items, water is the one that takes the most amount of energy to change its temperature. So the lower heat capacities that we have on this table means it heats up easily. And the higher heat capacities that we have in our table means that it doesn't heat up as easily. More energy is needed.